Good afternoon. Just picking up where we have left off, okay, making the transition from working with just algebraic expressions to working with algebraic equations. And again, the other day we looked into categories of equations, and among those we had conditionals, contradictions, as well as identities. And just for what we have in section R5, okay, just looking at identifying whether we have a conditional, contradiction, or identity. Now we have in number 24, okay, so we're working with a different variable in the letter n. And if we're looking at trying to solve, okay, for this letter and determining what type of equation we're going to have, okay, we have first of all working in what we have for n. Okay, so we have on the left-hand side, we have 4 times the quantity of 3 minus 5n, followed by the addition of 1 is equal to negative 4n minus 8 minus 16n, and working around the terms in the variable n. On the left hand side, I can distribute 4 over the quantity of 3 minus 5n, so this is going to be 12 minus 20n followed by the additional 1, and we have to the right, okay, we have negative 4n and negative 16n can be combined. And here we have negative 4 and negative 16 will be negative 20. So the combination of these terms, we have minus 20n minus 8. And for what we have on the left, okay, we have like terms with the constant values 12 and 1. And putting together, okay, so we have 13 minus 20n is equal to negative 20n minus 8, okay, and so we have two pairs of like terms, okay, with the constants 13 and negative 8, as well as the variable terms that we have in negative 20. And looking at combining like terms, and we can work with what we have in the variable n. Okay, so if I take care of the negative 20n on the left, I can just add 20n on both sides. And it turns out that the right hand side also has negative 20n, and guess what? We're going to have the n terms to cancel throughout. And so for what remains at this stage, okay, we have two numbers that will be said to equal each other, where we have the statement 13 is equal to negative 8. And if we have this outcome where we are trying to say that two numbers are equal to each other when in fact they are not, okay, it's going to turn out that for n, we're not going to have any solution. Okay, so you could always go back and try to plug in a 0 or a negative or a positive real value, and there's no input for n whereupon both sides of the equation will be equal. And so for what we have in this problem, okay, there is no solution. And again, arriving at the stage where we're trying to say that two numbers are said to be equal when in fact they are not, okay, this is a case of what we have with a contradiction. And for what we have in the next part, okay, and we have for number 26, okay, this time we're going back to the variable x. And in the case of number 26, okay, so we have on the left hand side, okay, we're going to have negative 5 plus 3x, and for what we have on the right, okay, we have a set of parentheses, and so we got negative 5 plus 3x is equal to 3 times the quantity of x minus 1 followed by the subtraction of 2, and looking at gathering what we have. Okay, so left hand side, so we have negative 5 plus 3x. So there were no like terms on the same side to combine on the left, and for what we have on the right, okay, so we have a distribution to perform. So 3 times the quantity of x minus 1, this will come out to 3x minus 3. We have followed by the subtraction of 2. Okay, so we have the terms on the left hand side waiting for what's going to happen on the right. Okay, so on the right we've had distribution, and now we have like terms with -3 and -2, and if we combine the constants on the right, so we got 3x as the only variable term in this location, and we have -3 minus 2, okay, will be -5. And so looking at what we have once again are going to be two pairs of like terms, and so as we look at combining what we have in x, just as we did moments ago with n, okay, so we got 3x on the left, and I can eliminate the presence of 3x by subtracting 3x on both sides, and it's going to turn out that we have not just like terms in x, but identical terms, and these are going to be canceled out. And so left standing is that after the x terms are eliminated, okay, we have numbers that are said to be equal to each other, where we have -5 is equal to -5. Now this statement is going to be true. Okay, so for what this is going to signal is that we're going to have an infinite number of solutions. So regardless of what you place for x, whether x is 0, or whether it is a positive number or a negative value, you're going to have both sides of the equation to ring true. Okay, so we have, in the case of the solution, you're going to have not just one value, but an infinite number of values. And there are various ways that you could write this. Okay, so we can say we have the set of all real numbers. Okay, so you have R for all real numbers, and again you could have what we refer to as interval notation, where you have parentheses around negative and positive infinity. And again, if you have with this type of equation coming down to both sides equal to each other, where we have an infinite number of values that can be applied for the variable we are solving for. Okay, this is going to be a case of what we have in an identity. All right. Now, for what we have in the case of number 28, and there's a part we're going to be looking into shortly. That would be rational equations. Okay, and in the case of 28, now there are terms that will have fractions for coefficients, and in this problem, okay, so we have looking at solving for the variable y. Okay, and so for the setup we have for number 28, okay, so we have 2/3 of y minus 5 is equal to 1/6 of y minus 4 and you could technically combine the y terms as they are, but you can also modify the coefficients where we can take care of the fractions in advance. Okay, so if you notice you had 2/3 as one fraction, 1/6 as the other, and we can just change the coefficients if we multiply all the terms out by the least common denominator. And the smallest number that both 3 and 6 will go into is going to be 6. So if I take all the terms and multiply by 6, okay, so we have 6 times 2/3 of y, and bring down the subtraction, and so we have minus 6 times 5 is equal to 6 times over 1/6 of y, and again bringing down subtraction, and we have minus 6 times 4. Okay. And so for the first product, okay, and you can go ahead and reduce along the lines of cross multiplying. I'm just going to extend this a bit. Okay, so think of like 6 over 1. 6 is 6 over 1 times 2/3 of y, that would be 12/3 of y, minus 6 times 5, which would be -30. 6 times 1/6 of y will be 6/6 of y, which will go to y. And we have minus 6 times 4, which we have with negative 24. Okay, so 12 thirds is 4. So we have 4y minus 30 is equal to 6 is 1, and 6 of y is going to be y minus 24. All right, so this time around we're back in a situation where we have two variable terms and two constants, where we have two pairs of like terms, and this time what we have in the variable, we're not going to have the same term on both sides as was the case with number 24 and number 26. And so we're not going to have complete elimination of the variable terms. And so for what we have in this arrangement, okay, so I can work with what I have in y. And my recommendation is to take out the smaller of the variable terms, and between 4y and y is going to be the lesser of the two. So I just take y away from both sides. And so we've got 4y minus y. Okay, so that would go to 3y. And we have 3y minus 30 is equal to negative 24. And looking at solving for y, so we're down to 3y minus 30 is equal to negative 24. And so I have the arrangements whereupon there exists a two-step linear equation. Okay, so for the first step, I can isolate 3y upon moving 30 by adding to both sides. And so we have for this arrangement, okay, so we've got 3y is on the left, and negative 24 plus 30 on the right comes out to 6. So you've got 3 times y is 6. And with division by 3, okay, it's going to turn out that for what we have in y comes out to 2. All right. And so this equation has one solution. Okay. And any equation that has a finite number of solutions, okay, like in this case, okay, this is going to be a conditional. Okay, so this particular equation is true on the condition that y is equal to 2. And again, so a condition is going to have a limited number of solutions, and in this case we have limited in the sense that there is one right result. All right, and now again we transitioned, okay, from the categories of conditional, contradiction, and identity, and made the segue over to working with quadratic equations. And for what we have, again, just for quadratic equations, and we have in standard form, again, a quadratic equation is going to be a second degree equation whose standard form, again, is going to be ax squared plus bx plus c is equal to 0. And again, whereupon we have the a does not equal to value. It's not equal to the value of 0. Okay, so we need that x squared term to exist. And now, for what we have in the case of quadratic equations, okay, now again, quadratic equations are not limited to just the variable x. And for what we have from the group of problems in section R5, now we have a quadratic equation in the case of 30, and this equation is in terms of the variable y, and we have in the opening statement, now we got y squared by itself is set equal to 18 minus 7y. Okay. If you notice, okay, we have a quadratic equation. Since we have the highest degree term in y is going to be y squared, and if I put this in standard form, like the standard form would be along the lines of ay squared plus by plus c is equal to 0, where any of a, b, and c could be positive or negative. And let's say that if I rearrange the terms, where we have this quadratic equation to be written in standard form. So what I can do here, so you have y squared is to x squared and y is to x, and if I move the 7y over and join with y squared, so we'll add 7y, and for plus c, the constant, this will be in reference to 18, so I can move the 18 by subtracting. And so in realigning the terms, I'm going to have y squared plus 7y minus 18 is equal to 0. And so we have this equation is in standard form, and we have the pathway to which we can use once again what is referred to as the zero product property. Okay, so I have a trinomial that is factorable into integer coefficients. So for y squared we have y and y, and for factors of negative 18 that will have a sum or difference on the plus side at 7. Okay, so negative 18 will have a plus and a minus factor, and I want the weights of the factors to be such that we'll have the sum or difference, okay, to be on the plus side at 7. So this means that we will have more weight on the side of the addition than what we have with the subtraction. In this case, we will have a y plus 9 and a y minus 2. Again, 9 times 2, negative 2 is negative 18. And adding together 9 and negative 2, we have 7. Okay. Now, with the zero product property, I can set each of the factors to 0. And with y plus 9 equal to 0, so we have y equal to negative 9 as one solution. And the other solution we have from setting y minus 2 equal to 0, and here we have that y is equal to 2. Okay, so for number 30, okay, y is going to have a couple of solutions, and if one happened to be wondering, this is another case of a conditional where we have two solutions. Okay, so this is true as long as we had that y is equal to negative 9 or positive 2. All right, now for what we also have as a quadratic equation, and that is also introduced outside of the standard form, we have in this time the letter z. We have in 34, we got z squared is equal to 25z. Okay. And I have a quadratic equation, but this one is not in standard form. Okay. And you have just, again, just for the counterparts now, z squared would be like in reference to x squared, and we've got 25z. Okay, that's going to be kind of fixated on the bx portion. And if you notice, we don't have any non-negligible constant in this equation. Okay, but I can set nonetheless the equation to 0. Okay, so I have z squared on the left, so that will like correspond with ax squared. And so what I can do here is that I can just move the 25z so we have with subtracting. So we have in the setup, now we got z squared minus 25z is equal to 0. And now, okay, so look at the terms carefully. Okay, so we have a second degree term and a first degree term, but we do not have a constant that follows. Now one might be inclined to factor out z plus 5 and z minus 5, but you're not going to do it in this case. And this would be if I had the difference of squares where I had z squared minus 25, but the roadblock here is the z alongside the 25. Okay, and so for z squared minus 25z, okay, we're going to have factoring out. Okay, the greatest common factor that exists is going to be z, and factoring out z. Okay, so z into z squared is z. Z into negative 25z is negative 25. And utilizing the zero product property, Okay, so we have the first factor z. If I set this to 0, well, we already had the first solution, and again, that would be consistent, like 0 squared is equal to 25 times 0. And for the other factor, okay, so we have the binomial z minus 25. And if I set this equal to 0, so z minus 25 equals 0, we're going to have that z is equal to 25. And again, 25 squared is equal to 25 times 25. And so z is going to have two possible solutions with 0 and 25. So you have another conditional that has a limit of two possible solutions, and those solutions being 0 and 25. Now, in the case of where we have just kind of fine-tuning, okay, where and when we can use factors or factored out expressions, and where we can directly apply the zero product property. Now, in number 35, okay, we have the variable to work with in the letter M, okay, and we have a factored out display in this problem, and we've got, see, we have the quantity of M plus 4 times that of M minus 5 is equal to -8. Okay, and one might be tempted to set each of these expressions equal to -8 and just solve, but remember, you're looking at trying to use the zero product property. Notice from number 30 and 34, when I had the factored form, we had 0 on the right hand side, y plus 9, y minus 2 to the left, 0 to the right, and we have z and z minus 25 to the left in problem 34, 0 to the right. So again, with -8, what we have on the right hand side must be 0. In order to use the zero product property. So there's a bit of an entanglement because we cannot use M plus 4 or M minus 5 directly, or at least with the way that they are laid out. Okay, so to sort of rearrange where we have the capacity, okay, to set the quadratic equation equal to 0, and we have to take care of the parentheses and go through the old exercise, foiling out the terms. Okay, and these expressions will be in the letter M as opposed to the letter X, but the same premise. Okay, so we have first product, we have M times M is M squared. Outside product, M times -5 will be -5M. Inside product, we'll have at 4M, and the last product we have at -20. And we have is equal to -8. Okay, so for what I have on the left, okay, so got M squared, -5M plus 4M becomes -M. Okay, so I still have -20 is equal to -8. And now I can reestablish where we have the standard form where I can have 0 on the right, and this will be made possible upon adding 8 to both sides. So we'll have in the rewrite, okay, so we have M squared minus M minus 12 is equal to 0. So we have a factorable trinomial expression Again, the first combination of binomials, I cannot use the zero product property since I did not have zero to the right. Now I do. Okay. So for m squared, we have going to m times m. And for factors of negative 12, okay, we have a plus factor and a minus factor, whereupon the sum or difference of the coefficients will be negative 1. So we have more weight given to the addition than to the subtraction. Okay, so we have with these factors, okay, we have m plus 3 and m minus 4, and since the product is equal to 0, I can itemize and set each of the expressions equal to 0. So in this case, okay, so if m plus 3 is equal to 0, so we have that m is equal to negative 3. And if we have that m minus 4 is equal to 0, okay, well, we're going to have that m is equal to 4. Okay, so we have two values in this case. So you have like yet another conditional with two solutions, and you could always go back and check. Okay, so if you have like in the original, if m is at 4, 4 plus 4 is 8, 4 minus 5 is negative 1, 8 times negative 1 is negative 8. Likewise for negative 3, negative 3 plus 4 is positive 1, negative 3 minus 5 is negative 8, positive 1 times negative 8 yields negative 8. So those values will check out. All right, now there is another technique that will involve solving what we have for quadratic equations. Okay, and where the zero product property might be somewhat limited in scope, there is another approach, and this is going to involve square roots. And I tell you what, let me give have a transition here. Just want to mention, okay, like in the case of perfect squares, say starting out with 1. Okay, so perfect squares have like 1 times 1 is 1. Next perfect square would be like 2 times 2, which is 4. So 1 is 1 squared, 4 is 2 squared, 3 squared with 3 times 3 is 9. 4 squared is 16. 5 squared is 25. And if we continue, and I was going to get up to 10 squared, it's about 36. 7 squared is 49. 8 squared is 64. 9 squared is 81. And 10 squared comes out to 100. And now there's some quadratic equations that might have radical solutions. And let me kind of mention some items here. Like if you were to reduce the following radicals, or expressed as a reduced radical. And so we have a first case. Okay, say we have something like the square root of 300. You just kind of start out with a large number, and what you can do just to kind of reduce the amount of work that's involved. Okay, so if you look for the highest perfect square that is divisible into 300, well, 100 is a perfect square number, and it will go into 300 3 times. Okay, so 100 is a perfect square, 3 is not, and as a radical, now 3 cannot be factored where we have other than the perfect square of 1. Okay, and so we have, so we got the square root of 100. We have times the square root of 3. and the square root of 100. Okay, so that will go to 10. And the square root of 3 cannot be reduced. So like the square root of 300, this will come out to 10 times the square root of 3. Now I'll show you another approach. Let's say that if one were to neglect 100, and say that, okay, we could say like, say if they start low, let's say have like 4 will go into 300 75 times. Okay, now 4 is the perfect square value. And you see we have square root of 4 times the square root of 75. Now for 75, not a perfect square, but it is the multiple of a perfect square that is greater than 1. And the highest of the perfect squares divisible into 75. Okay, that's going to be 25. So in this case, we have the square root of 25 times the square root of 3. And for the square root of 4, okay, that will go to 2. Square root of 25, that is going to be 5. And again, the square root of 3 is going to stay. And looking at the coefficients, we got 2 times 5, so that will be 10. And attaching the square root of 3. So again, through this route, a little bit longer since we did not factor out the greatest factor among the perfect squares like in the first instance, but you still have 10 times the square root of 3. And just the little case here, or like, let's say the square root of 48, or the square root of 48, and the highest of the perfect squares that we can take into 48, so it'll be 16, and 16 will go into 48 3 times, and the square root of 16 is 4, and attaching we have 4 times the square root of 3, and just kind of show, say for the square root of 48, and the other perfect square that will go into 48, okay, well that's going to be 4. So in this case, this will be like the square root of 4 times the square root of 12, and I'll just work on down. So we have the square root of 4. 4 is a perfect square. Now for 12, 12 is going to be 4 times 3. So the square root of 4, we can say it's the square root of 4 times the square root of 3. And we have 4 whose square root is 2. Again, we have the square root of 4, which is 2. We have times the square root of 3. And so we have here, we got, again, through this longer route, we have 4 times the square root of 3. Okay, now, for what we have with the next approach, or the next possible approach, for what we have in solving quadratic equations, and this is going to be what is referred to as the square root property of equality. Okay, and for what we have in the case of the square root property of equality, and since we're dealing with real numbers right now, say that if you have a general constant value p, say that if p is a non-negative value, and we have, let's say that x squared is equal to p, then what's going to happen here is that with the square root property of equality, as we go from x squared equal to p to just what we have in x, we're going to have that x is equal to plus or minus the square root of p, and just itemizing, so you have going to the square root of p as the positive solution, and for the negative possible solution we have with minus the square root of p. All right, and just taking what we have and putting back just the display of the perfect squares. Okay, and let's say that if you have with the square root property of equality, and it's kind of shorthand here, so if you see SRP, this will be the square root property of equality, or SRP for square root property. And let's say that if you have so if you're solving by using square root property of equality, and also reduce radicals where possible, or reduce radicals where they exist. Let's say one case, right? This is, we'll just start out with the difference of squares that you could otherwise solve by the zero product property. And we'll just go with the basic. We'll say we have x squared minus 36 is equal to 0. Now, technically, you can factor out x plus 6 and x minus 6 and then just use the zero product property. But if we're using the square root property, okay, so we're going to isolate what we have representing x squared. Okay, so what I'm going to do here is I'm going to move the 36 to the other side. And upon doing so, okay, so we have the x squared is equal to 36. Okay, so we got x squared represented by itself. Now p is going to be represented by 36. And if I go from x squared to x, what's going to happen with 36 will be taking plus or minus the square root of 36. And 36 is among our perfect squares. And we have plus or minus, and the square root of 36 is 6. So we have for this route, we have with our two solutions for x, okay, there's going to be negative 6 at the lower end and positive 6 at the upper. Now, and let's say that if we have a case, say we don't exactly have a difference of perfect squares. I'm just going to keep this where the variable term right now is going to be x squared. And let's say that if I have something like x squared minus, let's say instead of 36 we have 32. Say if I have x squared minus 32 is equal to 0. And I'm looking at utilizing the square root property of equality. Okay, so again, just as I got x squared by itself by moving the constant, and we'll do at least that bit of history all over again, but this time we're going to have situated that x squared is equal to 32. Okay, and again, we got x squared equal to 32. Now 36 is among the perfect squares, however 32 is not. And if I go from x squared to x with the square root property of equality, so right now in the initial stage we have the x is equal to plus or minus the square root of 32. And now 32, not a perfect square number, but 32 is one of those composite numbers where I can factor to where I'm going to have squares among the factors that will be greater than 1. So for what we have in the case of the square root of 32, okay, so if you look at your perfect squares, okay, you have 4 will go into 32, 9 will not, 16 will go into 32 2 times, 25 will not, and 36 we've already gone over. So between 4 and 16, okay, we'll go with the higher perfect square factor of 32. So that's going to be 16, and 16 will go into 32 2 times. So for the square root of 32, okay, this will be square root of 16, which is 4 times the square root of 2. Okay, so just relaying back, and it's going to follow that in reduced radical terms. We have the x is equal to plus or minus 4 times the square root of 2. And looking at itemizing, and I wish that Alex had it where you could just put in plus or minus, but here you have to itemize. Doesn't matter whether you put in the positive or the negative item first. And so say we have x is equal to 4 times the square root of 2. And again, for the other solution, that's going to be minus 4 times the square root of 2. Right. Okay, so far we've had, yes.
I got a question. So can we not just leave it as the plus or minus, or do we have to separate it out?
If this were a written exam, you could write it in combined terms. But I know in Alex, again, I wish Alex had that plus or minus feature. So with them, you would have to separate. But if it were like a written exam or whatever, you could have left it in combined form.
Okay, thank you.
Okay, now we have okay, now for x squared. Okay, now again, for the square root property, the x is like a general case, and the x squared, that does not have to be limited to just the square of a single letter. And I'll give you like a case of where we have just expanding the model a bit. And tell you what, let me I'm just going to copy this portion. Okay, now let's say if I have kind of a multi-term expression, and we'll say that we have let's say we have x minus 5 squared, and we'll say we have minus 60. Is equal to 0. Okay, so I have the square of x minus 5 followed by the subtraction of 60 is equal to 0. And working with this, okay, so if I isolate the squared variable expression, so it's not the square of x but the square of x minus 5. Okay, so here, okay, I can move the 60 by adding. Okay, so we have in this layout, okay, so on the left, and we have the square of x minus 5. is equal to 60. So I'm at this x squared is equal to p stage, but where x is represented by x minus 5. So in terms of going from the square of the expression to the first order, so you have like conceptually, say, have like x minus 5 or x minus 5 to the first. And to the right, we have 60 representing p. Okay, so we got x minus 5, and we have equal to plus or minus, okay, the square root of 60. And now 60, if you notice, okay, we do not have as a value among the perfect squares, but it is a number that will be a multiple of a perfect square that is greater than 1, okay? And for what we have in the case of the square root of 60, for the square root of 60. Now we got a fairly large number, but if you look at the numbers, okay, 49 will not go into 60, 36 cannot be taken directly into 60, 25 cannot, 16 cannot, nor can 9, but 4 will go into 60 15 times. Okay. So for the square root of 60, so I have the square root of 4 times the square root of 15. Okay, so this will go to 2 times the square root of 15. And so just putting back, so you have x minus 5. So this will be plus or minus 2 times the square root of 15. All right. Now we're still looking at solving for x. Okay, so we have x minus 5, okay, is equal to plus or minus, okay, 2 times, okay, the square root of 15. Now to get x by itself, we'll do here. So I want to get rid of the negative 5. So I'm going to add 5 to both ends. Okay, the way I'm going to lay this out, okay, so I'm going to add 5. And guess what? And I'm going to apply like plus 5 on the right, but I'm going to put this in front of the radical term. And if you notice, okay, so you have x minus 5 plus 5, and you have like 2 times the square root of 15 plus 5, but situating the addition of 5 in front, and just looking at consolidating. So x minus 5 plus 5. Okay, so that will go to x, and x is going to be where we have 5 plus or minus 2 times the square root of 15. And looking at itemizing, okay, since like in Alex, okay, since we don't have the plus or minus feature in that, okay, we can say that just separating in exact terms. Okay, so we're going to have 5 plus 2 times the square root of 15 at the upper end, and we have at the lower end, we have 5 minus 2 times the square root of 15. Okay, so those will be your exact results, okay, for what we have for this particular quadratic equation. All right, and for what we have in the case of taking from section R5, and there were a couple of problems we had concerning the square root property of equality. This is not what I had in mind. Okay, So just for the group of problems, okay, we have from section R5. And we have with numbers 40 and 41. Okay, so we got to change up in the variables. Now for number 40, okay, we got the letter V. Now we're looking at applying the square root property of equality. So right now we got 6v squared minus 30, okay, is equal to 0. And if we're looking at applying the square root property of equality, okay, so we're going to have v in place of x this time around. And so I got the square of v involved. Okay, so I isolate v squared just like x squared is isolated in the general case. And what I can do here is I can at least get the 6v squared by itself upon adding 30 to both ends. And so we have in this arrangement case, so I got 6v squared is equal to 30, and getting v squared by itself. Now I could have divided by 6 beforehand, but just doing it after isolating the variable term, I can now do it at this juncture. Okay, so now we got 6v squared over 6 becomes v squared, and v squared is equal to 30 over 6, which is 5. Okay, and 5, okay, is a prime number, and as I go from v squared to v, okay, so think of like x squared is represented by v squared, p is represented by 5, and going from v squared to v, just like x squared to x. Okay, now 5 is going to change over to where we have v is equal to plus or minus the square root of 5. 5 is not a perfect square, and the highest perfect square that will go into it is only 1. So we have the square root of 5 is already in lowest radical terms. So we have for v, if you itemize, we're going to have opposite sign values or additive inverses with negative and positive square root of 5. Okay. Now, and for what we have in 41, okay, so we have yet a different variable, and this is going to be with the letter k. And here we have this statement's k. So we have not the square of k, but the square of k plus 2. And that is set equal to 28. Okay, so you have the square of k plus 2 is equal to 28. Alright, so you can think of like the square of k plus 2 representing the square of x, and p being represented by 28. So if I go from the square of k plus 2 to just k plus 2, and plus or minus the square root of p is going to be plus or minus the square root of 28. And I will essentially rewrite this. I have k plus 2 equal to plus or minus the square root of 28. Now, 28, not a perfect square, but it is an even number that can be reduced in its square root. Now, some even numbers, a lot of even numbers can have, if they're not perfect squares to begin with, you can have radical reduction performed. Some of them you can, some of them one might think that you can, but it turns out upon examination that reduction can no longer further be carried out. But for the square root of 28, okay, this is one where we can reduce. And for the square root of 28, now the highest perfect square divisible into 28. So just looking at what we have for 28, Okay, so for numbers in proximity, 25 will not go into 28, 16 will not, 9 will not go into 28, 4 will. So the highest perfect square divisible into 28 is going to be 4. And 4 will go into 28 7 times. And for the square root of 28, that is reducible to 2 times the square root of 7. So we have, looking at what we have going back to the equation, we have that k plus 2 is going to be equal to plus or minus 2 times the square root of 7. And looking at expressing in terms of k by itself. And just to balance, okay, so if I get k by itself, so I'm going to take 2 away from both sides. Okay, and for 2 times the square root of 7, or plus or minus 2 times the square root of 7, if I take away 2, I'm just going to put the subtraction out to the front. Okay, so you got k plus 2 minus 2. Okay, so you're going to have a cancellation. Left-hand side becomes k. And to the right, so I have negative 2. And the other 2 is a coefficient of 2 times the square root of 7. Okay, so this is the compact notation for the final result. But again, if I itemize, okay, so we have at the upper end, we're going to have k equal to negative 2 plus 2 times the square root of 7. And we have at the lower end, we have k equal to negative 2 minus 2 times the square root of 7. And there will be other approaches we will have regarding solving quadratic equations. And I tell you what, just for what we have right now, at least with the square root property of equality, so if you're looking at solving by the square root property of equality and reducing the radicals. We'll say for the next few moments. Okay, let's see what we get for first case here, and we'll say that we have, let's say we have the square of x minus 3 minus 40 is equal to 80. Also, we'll say that we have that 2x squared let's say we have 2x squared plus 22 is equal to 122. Okay, so let's see what we get for x by utilizing the square root property, and also where you have radicals, reduce those as much as possible. Okay, for these items, okay, so if we're looking at solving by the square root property, okay, so we have with the first item, okay, so you have the square of x minus 3 minus 40 is equal to 80. And working with what we have, with the square root property of equality. Okay, so we got the square of x, okay, is represented by the square of x minus 3. And we want to isolate this, okay, in order to be able to identify p. Okay, so right now, okay, we can isolate the square of x minus 3, okay, by adding 40 to both sides. And upon doing so, okay, so we have the square of x minus 3 is equal to 120. Okay, and again, so I have p is represented by 120, square of x is represented by the square of x minus 3. And say if I go from just the square of x minus 3 to x minus 3, we will have to the right would be plus or minus the square root of p, which in this case will be the square root of 120. Okay, all right. I don't need the parentheses at this juncture. So we got x minus 3 right now is equal to the values plus and minus, okay, the square root of 120. Now, this is a case of where you're going to have nowhere as much radical reduction as one might be inclined to think. Now, we got a fairly large number with 120, and 120 factors out in all kinds of ways. 120 times 1, 60 times 2, 40 times 3. But if you look at the perfect squares, okay, like if I went beyond 100, next perfect square would be 121. Okay, but for the numbers out of the perfect squares divisible into 120, okay, 100 won't go into it, 81 will not, 64, no, 49, no, 36, no, 25, no, 16 will not, 9 will not. But in case of 4 is the highest perfect square divisible into 120, and that will go 30 times. And again, 30, even number, not a perfect square, and 16, 9, and 4, okay, signal that since those don't go into 30, the highest perfect square that will go into 30 is only 1. So just for the square root of 120, okay, for the complete radical reduction, that's going to be 2 times the square root of 30. And so just going back to our square root property of equality. So now we have on the left, we have x minus 3 is equal to plus or minus, and what is now going to be 2 times the square root of 30. And now getting x by itself. Okay. So I'm going to add 3 to both sides here. So I'm going to apply 3 at both ends. Alright. So you're going to have x minus 3 plus 3. Okay, the minus 3 and plus 3 will go out. So we got x. To the right, and we'll have 3 to apply to both plus and minus. Two times the square root of 30. And looking at separating. So we will have at the upper end, on the side of adding, we have 3 plus 2 times the square root of 30. And for what we have with the solution at the lower end, we will have 3 minus 2 times the square root of 30. Okay. Now, for what we have in the case of the other problem, okay, this is where we have the single variable term is at 2x squared. Okay, and we have with this problem, okay, so we got 2x squared plus 22 is equal to 122. And if I'm using the square root property of equality, so I'm going to get, first of all, the 2x squared by itself. So I'm going to take 22 away, and we're going to have in the rewrite, okay, so we're going to have 2x squared is equal to 100, and then getting in terms of just x squared and we have in dividing by 2. Okay, so 2x squared over 2 becomes x squared, and 100 divided by 2, okay, so that will be 50. And transitioning from x squared to x, so we have the x equal to plus or minus, okay, the square root of 50. And 50, not a perfect square number, but it is a composite number whose square root can be reduced. Okay, so we got the square root of 50, and the highest perfect square divisible into 50, so you got 49 will not go into 50, 36 will not, 25 will. So for the square root of 50, we have the square root of 25 times the square root of 2. Square root of 25 is 5. We have times the square root of 2. Okay. So we have in reduced radical terms, okay, so we have x is equal to plus or minus 5 times the square root of 2, and in the case of itemizing, okay, so we have x is equal to negative 5 times the square root of 2, as well as positive 5 times the square root of 2. Okay, all right. So we have, again, the square root property of equality is one possible route in terms of solving quadratic equations, in addition to the zero product property, and where we might have some limitations with those approaches, there is at least one more case. And again, just taking what we have for, again, a quadratic equation that is in standard form, again, we have ax squared plus bx plus c is equal to 0. Whereupon a does not equal to 0. Okay. And where you might not have the trinomial to be factorable, where you can directly use the zero product property, and also where the square root property of equality might not be so much a straightforward route. Okay, there is another approach, and this would be with the quadratic formula, and this would be like taking and rearranging what we have with a, b, c, and x in this equation, where we can solve for x. And it's kind of a long, convoluted route in terms of solving this equation. But for what we have in the case of x, we have for the expression, we have that x is equal to negative b plus or minus the square root b squared minus 4ac, and that's going to be all over 2a. And there is a pathway through what is referred to as the completion of the square, and we will look at this down the road, especially when we look at quadratic functions. Anyway, so this is the formula for we have in correspondence to this quadratic equation in standard form, and again, Same reason, since we're involving the same terms, a is still non-zero in value. And let's say that if you're looking at solving for x, and I'll show you a couple of equations. They will look almost identical. Now say we have 2x squared plus 7x plus 2 is equal to 0. Okay. Now this trinomial cannot be factored, and if you were to try factoring by grouping, okay, think of like multiplying the first and the last coefficients. 2 times 2 is 4, but for integer factors of 4 that are positive, we have like 4 and 1, 2 and 2. However, 2 and 2 add up to 4, 4 and 1 add up to 5, and neither combination will add up to 7. Okay, and to see if we have any solution, okay, first of all, we can go with the quadratic formula. Okay, so representing a will be the a squared term coefficient. So a is equal to 2. And since we have a positive 7x, we have that b is equal to 7. And since we have a plus 2, we have that c is equal to 2. And we have with the quadratic formula, if we are looking at substituting, okay, so filling in the numerical values. Okay, so we've got for negative b, then we have the negative of 7. And we have plus or minus the square root. Okay, now b squared, we have the square of 7. We have minus 4ac. So we have minus 4 times 2 times 2. And all over 2a, again with a at 2. So we have all over 2 times 2. Okay, now for what we have in following through, so we have for x, again we have negative 7 plus or minus the square root. Now 7 squared, or 7 times 7 is 49. Negative 4 times 2 is negative 8. Negative 8 times 2 is negative 16. In the denominator, so I have 2 times 2 is 4. And so we have negative 7 plus or minus what is going to be the square root of 33 all over 4. Okay, and if you were to itemize, okay, and square root of 33, that is already in simplest radical form. And so we have for the combination, okay, so we have on the side of addition, we have negative 7 plus the square root of 33 all over 4. And we have at the lower end, we have negative 7 minus the square root of 33 also over 4. And throughout, okay, what I have seen with applying the quadratic formula, most will get the negative b squared to a part route or portions correct. It's usually the negative 4ac that can trip many up. And let's say that, say if I almost duplicate this example, but just changing the key detail. And let's say that if I change up, okay, just Okay, so if I have like 2x squared instead of plus 7x, if I have a minus 7x plus 2 is equal to 0. So we have in the setup, so we got 2x squared minus 7x plus 2 is equal to 0. Almost, but not exactly duplicating the first example. Okay, so a is still at 2. Since we have 7x to be subtracted, it's going to follow that b is equal to negative 7. And we still have c at positive 2. And reapplying what we have with the quadratic formula. Okay. And this is where you had to be very careful with the sign values. Okay, so just filling in what we have now. Okay, so we got a at 2, b at negative 7, and c at 2. Let me go ahead and get this out of the picture. Okay, so we have filling in. Okay, so we got so for negative b, okay, now if you notice b is at negative 7, but I'm still having to apply the negative over b. So I'm looking at the opposite sign of negative 7. We have plus or minus, okay, the square root. And for what we have in the case of b squared, so we have the square of negative 7. And got minus 4ac, so it'll be minus 4 times 2 times 2 okay, and tell you what, yeah, we'll go with this. Okay, so we got over 2a, so that's going to be 2 times 2. And I'll tell you what, just to change one other detail, and this will not have much impact. Say if I have 2 negative terms in the mix. I'm sorry about this. Okay, so you got 2x squared minus 7x minus 2. So a is at 2, b is at negative 7, and we'll say this time that c is at negative 2. Okay. All right. So just substituting. Okay, so negative b, you have the negative of negative 7. 2a is still 2 times 2. b squared would have the square of negative 7. Now for the minus 4ac part, we got minus 4 times 2 times negative 2. And as we look at following through, okay, so for the terms in the numerator, okay, so you got negative of negative 7, this will be a positive 7. And got plus or minus. Now, for the square of negative 7, remember you have negative 7 times negative 7, which would be a positive 49. Now in your calculator, if you're squaring out a negative value, remember to put the negative term inside parentheses. If you don't, you'll have, like in this case, if I do not use parentheses, I would get a negative 49. But if you use parentheses around negative 7 and then square, we get the right amount, which would be 49. Now we got for negative 4 AC, we got negative 4 times 2 is negative 8. And this time negative 8 times negative 2 is going to be a positive 16. And we have 2 times 2 is 4. And narrowing it down, okay, so you got 7 plus or minus the square root. And 49 plus 16 is going to make 65. And this will be all over 4. And 65, okay, that number is already a completely reduced radical. And so we have just itemizing. We're going to have for x, okay, we have on the side of addition, we're going to have 7 plus the square root of 65 over 4. And at the lower end, we'll have 7 minus the square root of 65 also over 4. Okay. And so these are a couple of cases what we have with the use of the quadratic formula. Now, there is another part, okay, where you have also in section R5, and this will be in the case of what we have with rational equations. And for what we have regarding rational equations, okay, so we're going back to working with rational expressions. Okay, and for what we have in the case of rational equations, I'll give you cases here. Let's say that if you're looking at, let's say like in the case from section R5, okay, let's say if you have in number 68, okay, have a rational equation. And this one we're looking at solving for the variable t. So about 1/3 minus 4 over 3t is equal to 7 over t. Okay. Now, again, whatever I have in the solution, notice that t is in the denominator. And just some of the preconditions laid out, okay, just like the restricted values, okay. Okay, so you have like whatever we have for t. 3t cannot be 0, and t cannot be 0. Okay, if I had t at 0, I have 3 times 0 on the bottom, t would be 0 on the bottom, and I do not want a 0 denominator. Also, in the case of what we have with rational equations, okay, instead of combining rational expressions, I can clear out the fraction, every denominator throughout, and the least common denominator, okay, you have a blend of, okay, the smallest number that 3 will go into, so that's just going to be the number 3, and there's only one variable factor, and that is with t, and both appearances of t are in first order. So I can clear out the fractions. Now I'm known to be asked something like, when do you know to combine fractions and when to cancel out fractions? It is with the equal sign. So you're working with an equation. And if I multiply all the terms out by 3t, okay, so about 3t times 1/3 minus, going to have 3t I have times 4 over 3t I have is equal to 3t times 7 all over t. And just looking at what we have upon clearing out the fractions, so you got 3t times 1 is 3t over 3. Got minus 3t times 4 is 12t. Then we have over 3t. 3t times 7 is 21t over t. Okay, and so for what we have in this case, 3t over 3 is going to be t. minus, okay, we have 12t divided by 3t is 4, 21t over t is going to be 21, and for t minus 4 equal to 21, we're going to have that t is equal to 25, and we have with the restriction that t cannot be 0, and 25 is a non-zero value, so we have t is equal to 25. We'll check out. Now, where we have in our next rational equation type setup, and we have for number 74. Okay, so for 74, this time we have an equation in terms of the variable c. So 2 over c plus 3 minus 1 over c minus 3 is equal to 10 over c squared minus 9. Okay. Now we'll mention, now the work is going to get a little bit crowded. We've got 2 over c plus 3 minus 1 over c minus 3. And if you notice, we have a c squared minus 9 in factored form. We're going to have the quantity of c plus 3 times that of c minus 3. Okay. And just, again, some of the conditions we have. Again, whatever we have for c, we cannot have any of these denominators equal to 0. So c plus 3 cannot be 0, c cannot be negative 3. And if c minus 3 cannot be 0, c cannot be equal to 3 either. And if you notice, we have with the least common denominator. Okay, this is originated from c squared minus 9. So you got c plus 3, c minus 3. And the least common denominator, okay, we have with the product of c plus 3 and c minus 3. And again, we can solve for c, and so we can eliminate the presence of the denominators. So if we apply what we have, so I'm going to distribute the least common denominator over all of these terms. Okay, so I have c plus 3 times c minus 3. Okay, we have times the first expression case. I have 2 over c plus 3. I can bring down the subtraction. Okay, so I have c plus 3, c minus 3 times 1 over c minus 3. And we'll start doing some cancellations in a moment. Go to the right. We got c plus 3, c minus 3. Okay. So for what we got in the first round, okay, so looking along the lines of cross multiplying, you notice you got c plus 3 and c plus 3, so those will cancel out. For the next combination, okay, we have c minus 3 is going to go out, and to the right we have both c plus 3 and c minus 3. That third denominator set will also cancel out. So for what we've got left standing, we've got c minus 3 and 2. And we've got next, okay, so if you notice, okay, we got c plus 3 times 1, because you got subtraction, and the subtraction is going to be distributed over all of c plus 3. And to the right, okay, I have only the number 10 left standing. Okay, and looking at distributing, so about 2c minus 6, and distributing subtraction over what was left over with the quantity of c plus 3, so we'll have minus c minus 3 is equal to 10, and just combining 2c and negative c, so we have c, negative 6 minus 3 is negative 9, and we have that c minus 9, okay, is equal to 10, and upon adding 9, we have that c is equal to 19, and this will satisfy the restrictions of where c is not negative 3 or positive 3. So 19 is going to be the unique solution that we have in the case of the letter C. And now, just case of what we have with rational expressions, and this one, let's say I have this as a remaining example case. If you're looking at solving for x, and we'll say that we have we have 3 over x plus 2 and say we have plus plus 7 over x plus 2 is equal to 5 over x. Okay. So for what we're going to have here is we got 3 over x plus 2 plus 7 over x plus 2 is equal to 5 over x. And if you notice, okay, we have like denominators with the first and second terms, so I can go ahead and cluster together 3 over x plus 2 plus 7 over x plus 2. Okay, and in terms of working out what we have here, now preconditions we have for x plus 2 cannot be 0, so x cannot be negative 2, so that's one restriction, and the other restriction is that x cannot be equal to 0. So just kind of, okay, so x cannot be negative 2 or 0, and again for the least common denominator, and if you've seen proportions where you can multiply alternating numerators and denominators, that's fine. Okay, but I'll just kind of take the least common denominator here. So if I multiply x plus 2, I have times 10 over x plus 2. And to the right, okay, so I have multiplying out. Notice we have in taking the products between the least common denominators and the ratios. Left hand side, have x plus 2's to cancel. Right hand side, okay, we have x to cancel. So for what we have on the left, okay, so we have x times 10, or 10x. And we have this equal to 5 times the quantity of x plus 2. And distributing, okay, so you have 10x is equal to 5x plus 10. So you got 10x to the left, and I can join that with 5x. So I got 10x minus 5x becomes 5x. And 5x is equal to 10. And we have with division by 2, or should I say division by 5, okay, the quotient is going to be at 2. So you have x is equal to 2. And the restrictions that x be not negative 2 as well as 0 are satisfied. Okay, so they're another case of a rational equation. And in this case, we have the unique solution at 2.